Today we've come to the last section on quadratic residues. We are going to look at an application of quadratic residues. Now this application relates to Diophantine equations. So before we go into the application, let's see what is a Diophantine equation. A Diophantine equation is an equation which has integer solutions. All of you are familiar with Pythagorean triples, that is sets of integers which satisfy Pythagoras theorem x squared plus y squared equal to z squared. For instance, 3, 4, 5. 3 squared plus 4 squared equal to 5 squared. And therefore that satisfies x squared plus y squared equal to z squared. Now we are going to focus on we are not going to talk about Diophantine equations in general. It can be shown that not all Diophantine equations have solutions, and therefore we are going to look at a very specific class of Diophantine equations. Equations of the form y squared is equal to x cubed plus k. Again, even for this class there is no general method to solve all instances, and therefore we are going to use quadratic residues to find a set of values of k for which this equation has no solutions. Now, so therefore we are coming to the last theorem in this section. The Diophantine equation y squared is equal to x cubed plus k has no solutions if k is of the form 4n minus 1 the whole cube minus 4m squared, where m and n are integers such that no prime p congruent to 1 mod 4 divides them. Now we are going to prove this theorem using contradiction. That is, I am going to assume that I can find a set of integer values x and y such that y squared is equal to x cubed plus k, and k is of the form 4n minus 1 the whole cube minus 4m squared. Now obviously when I take modulo m, this value 4n minus 1 the whole cube minus 4m squared is going to be congruent to minus 1 mod 4, and therefore y squared is equal to x cubed plus k is reduces to y squared is equal to x cubed minus 1 when I take modulo 4. Now, so k is congruent to minus 1 mod 4. Now, I know that y squared is congruent to 0 or 1 mod 4 for any y. Why? Because I can list out all the possibilities. If y is congruent to 0, then y squared is also 0. If y is 1, y squared is 1. Even y is 2, y squared is 4, which is congruent to 0 mod 4. And when y is 3, y squared is congruent to 1, which is because it's 9. 9 becomes 1 mod 4. And so this equation y squared congruent to x cubed minus 1 mod 4 can be satisfied only when x is congruent to 1. Why? Again we can look at all the possibilities. If x is 0 or 2, you get when I put x is equal to 0, this becomes y squared is equal to 0 minus 1 or 3, and again when I put x is 2, I get 8 minus 1 again, which is 3. So x congruent to 0 or 2 gives me y squared is congruent to 3 mod 4, and x congruent to 3, when I put x congruent to 3, this becomes 27 minus 1 26, therefore y squared is congruent to 2 mod 4. Now both these possibilities, y squared cannot be equal to 2 or 3. We said that here y squared can be only 0 or 1, and therefore the only possibility is that x is congruent to 1 mod 4. Now I am going to take a as 4n minus 1. Then k is equal to a cube minus 4m squared. And therefore y squared plus 4m squared is equal to x cubed plus a cubed. I am just substituting back in that equation. And now this x cubed plus a cubed, of course I know, can be written as x plus a into x squared minus ax plus a squared. Now I know that x is congruent to 1 mod 4 and a is congruent to minus 1 mod 4. And so x squared minus ax plus a squared is congruent to minus 1 mod 4 when I substitute here. Thus, x squared minus ax plus a squared is odd and all its prime factors cannot be congruent to 1 mod 4. Therefore, some prime p congruent to minus 1 mod 4 divides x squared minus ax plus a squared, and hence p also divides y squared plus 4m squared. Hence, y squared is congruent to minus 4m squared mod p for some p congruent to minus 1 mod 4. But we said that p does not divide m by our assumption, and therefore minus 4m squared over p is equal to minus 1 over p is equal to minus 1. But this is a contradiction, and hence the Diophantine equation has no solutions when k is of the form 4n minus 1 the whole cube minus 4m squared.